This is the linear inequality video solutions. We're going to try to graph numbers that are greater than 7. That means x is an arbitrary number. This is our greater than sign in red, and this is the reference number 7. So together, we want to graph numbers that are greater than 7. We're going to first have to start by locating where a positive 7 would live on our real number line. Positive 7 is to the right of 0. All positive numbers are to the right of 0. So a 7 could possibly live here. Since we're trying to describe numbers that are strictly greater than 7, we're going to need to shade all those numbers that are to the right of 7, because larger numbers live to the right. This is simulating the description of numbers that are bigger than 7 because they are to the right. Because this inequality symbol is a less than symbol. We do not include the number 7 because 7 is not greater than 7. 7 equals 7. So we're going to indicate do not include the 7 by using this parentheses. This concludes the graph of all real numbers greater than 7. We are going to describe numbers that are greater than or equal to 7. Arbitrary numbers x greater than or equal to the value 7. We're going to first start off by locating where the number 7 lives on our real number line. Since 7 is positive, it's to the right of 0, possibly here. Numbers that are greater than 7 live to the right of 7. We're now going to shade all the numbers to the right of 7 because that's describing the numbers that are greater than. This is that simulation. Because our inequality symbol is a greater than or equal to, we're going to use the square bracket to communicate to the reader that we are going to include the number 7 in this description. This is describing the set of all numbers x that are greater than or equal to 7. This is the graph. You might be interested in set notation. Set notation uses the format that says the following. This is a set of all real numbers x such that. This vertical line means such that. We are now going to describe the numbers, and the numbers are greater than or equal to 7. Here's our set notation. Question 5. We're going to try to describe on a graph by shading the numbers that are between -5 and -1. We're going to first have to start by locating where both -5 and -1 would be on the real number line. If I go to the left of 0, -1 might be here, and further to the left I'll reach -2, -3, -4, and finally -5, possibly over here. We're going to try to describe numbers that are really between -5 and -1 because this value of x here represents arbitrary numbers, and they're arbitrary numbers that are between the -5 value and the -1 value. So as we shade now in black or gray, we're going to shade between -5 and -1. Now because our inequality signs have an equality, that means it's a less than or equal to. Less than or equal to. We're going to use the square brackets to communicate to the reader that we are going to include the values -5 and -1. This here is the graph of this inequality. You might be interested in set notation. The set of all x such that we're now going to describe what the values should be. They are numbers between -5 and -1. This is how we describe numbers that are between two numbers. In this case, the values are, in red, -5 and -1. In the graph, all of these numbers are between -5 and -1. We are looking at a shaded graph of numbers that are bigger than -4. That's because every number to the right of -4 is shaded here on the real number line. What we're doing here is also notating that we do not include the number -4 because this is a parenthesis. So if I'm going to describe this inequality, x represents all the arbitrary numbers that are shaded, and we're going to describe this as being greater than -4 because all the numbers to the right of -4 are shaded. Larger numbers live to the right. Larger numbers to the right of -4 are shaded in this picture. Now, if we want to describe this in terms of set notation, we have the set of all x, such that, let's actually describe these numbers. This here is our description. They are greater than -4, and we're going to close our parentheses. This here is our set notation. Interval notation is going to also describe what is being shaded. And for interval notation, we're going to start with this process by describing things left to right. That is, consider looking at this picture from left to right. What is shaded starts at -4 in some sense and continues all the way to the right of -4. That continues all the way to infinity. Now, infinity is not a number, it's an idea. We could never assume the value of infinity, so we're going to use this parentheses just to describe just that. And because we did not include a -4, we also use our parentheses around that -4 as well. So what you're looking at is the shaded graph in terms of set notation and now interval notation. Number 9, we are looking at a graph of numbers that are shaded to the left of -3. Now, those arbitrary values that we call x that are to the left of -3 are smaller than -3 because smaller numbers live to the left. And in this case, smaller numbers to the left of -3 are shaded in this picture. Now, because as the bracket is here, the square bracket, that means we include the value of -3. And so the symbol you're looking at is the less than or equal to symbol. It is strictly smaller than -3, and it also equals -3. And this is a description of the numbers that are shaded in your graph. In terms of set notation, we formally write the set of all real numbers x such that. This line that's vertical means the word such that. What comes next is our description. Those numbers are less than or equal to -3. This is your set notation. Interval notation starts by describing the shaded region in terms of left to right. All the way to the left, we have a shaded region. So we're going to start here by describing this as -infinity. And as we move to the right, we stop at -3 in terms of our shading. Because we have a square bracket, we use the square bracket to describe that we include -3. Infinity is not a finite number, so we always use the parentheses. This here is interval notation. Number 11. We're going to solve and graph a linear inequality. What you're looking at is A is a variable and 12 is being added to A, and that is less than 19. This is the phrase we start with. To isolate A, we're going to have to subtract 12 from both sides of this inequality symbol. We want to preserve our balance, so what we do to the left, we have to do to the right. On the left side, we simply have A. The positive 12 and the negative 12 cancel. We have A is less than 19 minus 12 on the right side of the inequality, and 19 minus 12 is 7. We have actually solved the inequality. But the graphing portion requires us to describe the numbers that are less than 7. Now 7 is positive, so it's to the right of 0 where all the positive number lives. And now numbers that are less than 7 are going to live to the left of 7, because smaller numbers are to the left, and smaller numbers that are smaller than 7 are simply to the left of 7. This describes the graph. Because we do not include 7, we're going to use the parenthesis sign. That communicates to the reader, simply do not include the value 7. This is the graph. Number 13. We're going to solve this linear inequality for t, and then we're going to graph the solution. We're going to start by subtracting 2 from both sides in order to preserve our balance, and we'll end up with negative 4t greater than or equal to negative 5t plus 14 minus 12 gives us plus 12. We're now going to add 5t to both sides so that we end up with, on the left side, t being greater than or equal to, our negative 5t and our positive 5t will cancel. We have t is greater than or equal to 12. We are now going to graph. 12 is positive, so it's to the right of 0 where all the other positive numbers live. Because our inequality sign is greater than or equal, we're going to now shade all numbers that are greater than 12, and those are numbers that live to the right of 12. These are numbers that are greater than 12. You're going to notice that we also have the equality sign. This is greater than or equal. So we're going to notate that we're going to have to include 12 in our graph by using the square bracket. What this means is to include the value of 12 as our solution, because t is greater than or equal to 12. This is the graph. Number 15. We're going to solve for x for this linear inequality by adding 1 over 21 to both sides in order to be fair. On the left side, we get x because negative 1 over 21 plus positive 1 over 21 is 0. And x will be greater than negative 4 over 21 plus 1 over 21 will give us negative 3 over 21. We're going to have to reduce this fraction. So we're going to note that, first of all, 3 in the numerator is prime and we can't break it down. But the denominator can be broken down as 3 times 7, where my 3's cancel, and the 7 is left in the denominator position. So we keep that in the denominator position. What's on top is the number 1. So we're looking at the values of x that are greater than negative 1 over 7. This is what we're going to have to sketch. This is what we have to graph. Now the fraction negative 1/7 is to the left of 0 where all the other negative numbers live. And describe numbers that are greater than negative 7, we are now going to have to shade all those numbers that are greater. They're the numbers that are to the right of negative 1/7. Because this is a strict inequality, strictly greater than, we're going to use the parentheses to communicate to the reader that we simply do not include the value of negative 1/7. This is the graph. We're going to solve this linear inequality for b. Now, this is problem number 17, and b is being divided by 2. So we're going to have to undo the division by 2 by multiplying both sides by 2. Being fair and preserving our balance, the 2's will cancel on the left. We have b is greater than or equal to the value 8. In order to graph this, we're going to have to locate where 8 lives on the real number line. Since 8 is positive, it lives with all the other positive numbers, which is to the right of 0. We're now going to have to describe numbers that are greater than or equal to 8. Numbers that are greater than 8 live to the right of 8. We're now going to have to communicate to the reader that we actually include the value 8 because this is a greater than or equal to sign. This is the graph of numbers that are greater than or equal to 8. Number 19. We're going to solve for x, this linear inequality. A negative 2 is being multiplied to x, so we're going to undo the multiplication by dividing. On the left, the negative 2's will cancel, and we're left with x. Now, because we divided by a negative, we're going to have to switch direction of our inequality symbol from less than to greater than. We now have some arithmetic to do. We have to note that 1/7 divided by negative 2 can be written as 1/7 times 1 over negative 2. When we multiply our fractions, we get 1 over negative 14. So that our inequality becomes x less than negative 1 over 14. We're going to now have to graph. Negative 1/14 is to the left of 0 where all the other negative numbers live. We're going to now have to describe numbers that are bigger, that are greater than the negative 1/14, and larger numbers live to the right, meaning numbers that are larger than a negative 1/14 will be to the right of negative 1/14. This is where we shade. Our inequality symbol is strictly greater than. So we're going to use the parentheses to communicate to the reader that this is really greater than. We do not include negative 1/14. Number 21, we're going to solve this linear inequality for x. We're going to start by adding 3 to both sides to be fair and preserve our balance. And we get negative 4x is less than or equal to negative 5x plus 10. We're now going to add 5x to both sides. To be fair, preserve our balance. On the left side, we get negative 4x plus 5x, which gives us an x, which will be less than or equal to Negative 5x plus 5x is 0, the value 10. We're going to now have to graph. We're going to have to graph and describe numbers that are less than or equal to 10. Since 10 is positive, it might live here where all the other positive numbers live, which are to the right is 0. We're now going to have to shade and describe numbers that are less than 10. Numbers less than 10 live to the left of 10. Smaller numbers live to the left. Because of the fact that our inequality symbol is less than or equal, we're going to include the 10, and we communicate that by using the square brackets. This is the graph of our linear inequality. Number 23. We're going to solve this linear inequality for x. On the left side, you notice that we can simplify. There's a constant negative 112 and a positive 8. These terms are like. We can combine them. Negative 12 plus 8 is negative 4. Minus 5x is greater than or equal to negative 5x minus 3. We're now going to add 4 to both sides. To be fair, preserve our balance, and we're going to simplify. Negative 4 plus 4 is 0. We're going to end up with negative 4x greater than or equal to negative 5x. And on the right side, we have negative 3 plus 4, which is positive 1. We're now going to add 5x to both sides. Now negative 4x plus 5x is going to give us our x greater than or equal to negative 5x plus 5x cancels on the right side of the inequality, so we end up with just the number 1. X is greater than or equal to 1. We're now going to graph. 1 is positive, so it lives where all the other positive numbers live, which is to the right of 0. Because these numbers are greater than or equal to 1, we have to shade the numbers or describe numbers that are greater than 1. Larger numbers live to the right, and larger numbers than 1 are to the right of 1. Because this is greater than or equal, we're going to use the square bracket to communicate to the reader that we include the 1. This is the graph. Number 25. We're going to solve this linear inequality for y. We're going to subtract 9 from both sides. To be fair and preserve our balance, we end up with 6y greater than or equal to. Now 75 minus 9 is going to give us 66. We're now going to divide both sides by a positive 6 so that the 6 cancels. On the left, we end up with y being greater than or equal to 11. We have solved this linear inequality. To graph this, we're going to have to locate the number 11 on our real number line. Now 11 is positive, so it lives with all the other positive numbers which are to the right of 0. To describe numbers that are greater than 11, we're going to have to shade numbers that are to the right of 11 because larger numbers live to the right. Because our inequality sign is a greater than or equal to sign, we need to use the square brackets. This is the graph. Number 27. We're going to solve this linear inequality for y. On the left side, we're going to use the distributive property to remove our parentheses. Negative 4 times 2y is negative 8y. Negative 4 times negative 17 is positive 68. This is less than negative 12y plus our 36. We're now going to subtract 68 from both sides. This is to be fair and preserve our balance. We end up with negative 8y on the left being less than negative 12y. We got plus 36 and minus 68. In other words, positive 36 and a negative 68. We're going to end up with negative 32. We're now going to add 12y to both sides to preserve our balance, and we'll end up with 4y being less than negative 32. Divide both sides by 4. We end up with y less than negative 8. We have solved this linear inequality. We're now going to graph this linear inequality. We're going to try to describe numbers that are less than negative 8. Negative 8 lives to the left of 0, where all the other negative numbers live. Numbers that are less than negative 8 are numbers that are smaller than negative 8. Smaller numbers live to the left. That is, to the left of negative 8. Because this inequality symbol is strictly less than, we're going to use a parentheses to communicate to the reader that we do not include negative 8. This is the graph.